Hi everybody, welcome to this video on Riemann sums and definite integrals. This is our 6th video in our video series on integration. In this video, we're going to learn about a type of sum called a Riemann sum. We'll then learn about definite integrals, which are a limit of a Riemann sum of a continuous function on a closed interval. To understand the definite integral, we're going to use limits and the concepts of continuity and discontinuity. If you'd like to revise the above topics, please see my video on limits in my Introduction to Calculus video playlist. So, what we're going to do is, initially, we're going to talk about sigma notation. And we're going to use this sigma notation to describe Riemann sums. And then we're going to use Riemann sums to describe definite integrals. So initially, to have a quick recap of sigma notation. We can use sigma notation to write large sums in a compact way. If we have a look at this equation here, the notation on the left of the equal sign, that is sigma notation, and it's describing the sum of all of the numbers shown on the right of the equal sign. So we can imagine that if we were summing a very, very large number of terms, we can be more efficient by just writing the sigma notation. So in this notation, the Greek capital letter sigma stands for sum. The index k, that tells us where to begin and where to end the sum. If we have a look at this sigma notation at the bottom of the screen, the symbols below the Greek capital letter sigma, that tells us where to begin our sum at k is equal to 1. And the symbols above the capital letter sigma, that tells us where to end our sum at k is equal to n. So the symbols to the right of the capital letter sigma, that's what we're actually going to be summing. So in this particular example, we'd start with k is equal to 1, and that'll give us a underscore 1, and then we'd increment our k value. So we'd increase our k value by 1. So k would become k is equal to 2. So then we'd have a underscore 1 plus a underscore 2. And then we'd keep incrementing our k value until we reach our end value, which in this case is n. So for example, we might have a sum of a underscore 1 plus a underscore 2 plus a underscore 3. And so on up until a underscore n. And just to finish talking about sigma notation, we'll just quickly look at these two examples. We can use sigma notation in different ways. Here in this first example, this is the sum from k is equal to 1 to k is equal to 6 of k. So here we'd start with k is equal to 1, and we'd increment and get k is equal to 2, increment our index again, we'd have k is equal to 3, and we keep incrementing that index by 1 until we get k is equal to 6, and we sum all of those k's. So we get 1 plus 2 plus 3 plus 4 plus 5 plus 6, and that gives us 21. Here on our second example underneath, we got the sum from k is equal to 1 to k is equal to 3. And this time, we're summing 2 to the power of k. So we start with k is equal to 1, and we have 2 to the power of 1. We increment our index by 1, and we have k is equal to 2. So we have 2 to the power of 2, and so on to 2 to the power of 3. So we're summing 2 to the power of 1 plus 2 to the power of 2 plus 2 to the power of 3, which is 2 plus 4 plus 8, which gives us 14. So we can see here that we can use sigma notation to write potentially quite a large sum of terms in a very compact way. So moving on to describe Riemann sums. To describe a Riemann sum, we start with a function f of x, defined on a closed interval from a to b. And if we have a look at our plot here on the right hand side of the screen, that's what we have. In this plot we've got the plot of y is equal to f of x, so that function f of x has been plotted and highlighted in blue, and f of x has been plotted from x is equal to a to x is equal to b on that interval. So our function can have negative values as well as positive values, or it could have all positive values, or it could have all negative values. In either case, we can still construct a Riemann sum with that function. So the next thing that we do is we divide up or partition the closed interval from a to b into n subintervals. So to do this, we choose n minus 1 points, x1, x2, x3, all the way up to xn minus 1, between a and b, so as that a is less than x1, x1 is less than x2, x2 is less than x3, and so on until xn minus 1 is less than b. And if we have a look at our plot on the right hand side of the screen, you can see that we've done this here. So we've chosen our x1, x2 and x3 points throughout, and so on, throughout the interval up to b. Now we represent a with x0 and b with xn to make the notation more consistent. And if we have a look at our plot, you can see that these changes have now been made. And we call the set p equal to x0, x1, x2, and so on to xn. We call that the partition of the closed interval from a to b. That partition p defines n closed subintervals. So our first subinterval is from x0 to x1, and our second subinterval is from x1 to x2, and so on up until the nth subinterval from xn minus 1 to xn. One of the closed subintervals from xk minus 1 to xk can be referred to as the kth subinterval of p. And we can see this here in the middle figure at the middle of the screen. We can see here that we've got our first subinterval from x0 to x1, our second subinterval from x1 to x2, our third subinterval from x2 to x3, and so on. And then highlighted in green, we have our kth subinterval from xk minus 1 to xk, and so on until our nth subinterval from xn minus 1 to xn. The length of the kth subinterval is delta xk, which is equal to xk minus xk minus 1. And we can see this here at the bottom figure at the bottom of the screen. So here we can see that the length of the first subinterval, delta x1, is x1 minus x0. The length of the second subinterval, delta x2, that's equal to x2 minus x1. And the length of the kth subinterval, delta xk, that's equal to xk minus xk minus 1. And the length of the nth subinterval, delta xn, that's equal to xn minus 1. So the kth subinterval, that can be used to refer to one of the closed subintervals. Next, inside each subinterval, we select a number from the x-axis, and the number from the kth subinterval is referred to as ck. And we then make a rectangle from the base of each subinterval and the height of the number f of ck. So if we have a look at the plot here on the right hand side of the screen, we can see that we've just done that in our plot here. So if we have a look at our first subinterval from x0 to x1, we've selected an x value on the x-axis within that first subinterval, and we've called it c1. Then we've calculated the corresponding function value, the corresponding y value for that c1 value, which is f of c1. And that point, c1, f of c1, that's been highlighted with a red dot on the plot. And then what we've done is we've made a rectangle from the base of that first subinterval and the height of the number f of c1. And then we've done something similar for the second subinterval. We've selected an x value from the x-axis within that second subinterval, and we call it number c2. And then we've worked out the corresponding y value for that x value, f of c2, and we've highlighted the point c2, f of c2 in red on the plot. And then we've made a rectangle from the base of that second subinterval and the height of the number f of c2. And what we've done is we've gone along and done that for each of the subintervals, creating rectangles for each one. The next thing that we do is that for each subinterval we calculate the product f of ck multiplied by delta xk. So that f of ck, that corresponds to the height of that rectangle for that subinterval, and the delta xk, that corresponds to the length of the subinterval, or the rectangle width. Now this product f of ck by delta xk, this is going to be positive. Well, this can be positive, negative, or zero, depending on whether f of ck, the height of that rectangle, depending on whether that's positive, negative, or zero. So just to reiterate that, for each subinterval we calculate the product f of ck multiplied by delta xk. And this can be positive, negative, or zero, depending on whether f of ck is positive, negative, or zero. And then what we do is we take the sum of the products for all of those subintervals. So our sum here in this maths equation here, s underscore n, is equal to the sum from k is equal to 1 to k is equal to n of f of ck multiplied by delta xk. And this sum is a Riemann sum for the function y is equal to f of x on the interval from a to b. And its value depends on the partition P and the choice of numbers C, K. So if we have a look at our plot here on the right hand side, we can imagine how the value of the Riemann sum would change depending on how we've created our partition and how we chose our numbers, our CK numbers. Because if we say created our subintervals to have, say, shorter lengths, or if we created our subintervals to have, say, larger lengths, or if we selected our ck values in a slightly different position, and that corresponded to different f of ck values, then we'd expect that our product for each subinterval, that f of ck multiplied by delta xk value, that would change, because our value of f of ck would change and our value of delta xk would change. So the value of the Riemann sum, that's going to change depending on how we create our partition and on how we choose our ck number for each interval. So what we can do is we can make the widths of the subintervals smaller and smaller using more and more rectangles. And we're going to do that now. If we have a look at the plot on the right hand side, you can see that right now we've got the partition that we had previously. But what we're going to do now is we're going to make the lengths of those subintervals smaller, and we're going to use a larger number of rectangles. And as we do this, watch how the rectangles approximate the region between the curve and the x-axis. So we're going to change that partition now. So now we have shorter subinterval lengths and we have a larger number of rectangles. And we can do this again. We can shorten our subinterval lengths further, and we can use an even further number of rectangles. And as we do this, watch how the rectangles approximate the region between the curve and the x-axis. So we've just shortened our subintervals further there, and we've used a large number of rectangles. And as we watch that process, the rectangles approximate the region between the curve and the x-axis with increasing accuracy as those subinterval lengths get shorter and the number of rectangles increases. The Riemann sums have a limiting value as the lengths of the subintervals approach 0. The longest subinterval length of the partition P, that's called the norm of the partition, and we write it as the capital letter P between two pairs of parallel lines. The limit of the Riemann sum of the function as the norm of the partition approaches 0, as the length of the longest subinterval approaches 0, that is the definite integral of the function. So just to reiterate that, the limit of the Riemann sum of the function as the norm of the partition approaches 0, as the length of the longest subinterval approaches 0, that is the definite integral of the function. The definite integral is the limit of a Riemann sum of a continuous function on a closed interval. All continuous functions are integrable, and if a function f is continuous on an interval, a closed interval from a to b, then its definite integral over from a to b exists. Using mathematics, the definite integral can be described as the limit as the norm of the partition approaches 0 of the sum from k is equal to 1 to k is equal to n of f of ck multiplied by delta xk. And that is the definite integral. So we can develop this further. We can describe the area under a curve under certain conditions as being equal to a definite integral. And we can develop this further, and we're going to discuss this a little bit further now here, and we're going to tie it back to some of our previous material. We've seen in our previous video, making estimates with finite sums, that we can approximate the area under the curve of a non-negative continuous function using finite sums. If we have a look at these plots here at the bottom of the screen, what we've got are plots of speed versus time. So here in this plot, speed is equal to time squared. And we've got that function, speed is equal to time squared. We're plotting that on our closed interval from time is equal to 0 to time is equal to 5 seconds. And what we've done is we've highlighted the area underneath the curve in blue. So what we tried to do previously is we tried to approximate the area underneath this curve with the sum of a number of with the sum of the areas of a number of rectangles. And what we did was initially we divided up the interval from 0 to 5 seconds. We divided that up into a number of sub-intervals. So here in our first plot at the bottom left of the screen, we divided up the interval from 0 to 5 seconds into 2 sub-intervals. And in that first sub-interval, we approximated the area underneath the curve with the area of a rectangle, which is outlined in red. And then in our second sub-interval, in that bottom left graph, we approximated the area under the curve with the area of that second larger rectangle, which is again outlined in red. And then we approximated the total area underneath the curve as the sum of the area of the two rectangles. And then moving on to our second middle plot, we essentially did the same process but with a larger number of sub-intervals. So we divided up our interval from 0 to 5 seconds into 5 1 second intervals, and we approximated the area under the curve in each sub-interval with the area of a rectangle. And then we approximated the total area under the curve with the sum of the areas of the rectangles. And then we did that again in our third plot, but this time with even shorter sub-interval lengths, with a sub-interval of a half a second. And what we saw in our previous video was that the approximation of the area under the curve using the rectangles got closer and closer to the true area under the curve as the length of the sub-intervals decreased and as the number of rectangles increased. So what we were actually doing there was we were creating a Riemann sum. We were dividing up our interval from 0 to 5 seconds into a series of sub-intervals. And then we were selecting a function value within each sub-interval, and we were calculating the product of the length of the sub-interval, which is the base of the rectangle, multiplied by the function value, which is the height of our rectangle for that particular sub-interval. And then we were summing the product for each sub-interval. So for each sub-interval, we were summing the product of the base by the height. Delta xk, the length of the subinterval, multiplied by our function value, f of ck, the height of the rectangle. So when we were doing this in the previous video, we were actually creating Riemann sums with different subinterval lengths. So the area under the curve, it is estimated with a sum of function values multiplied by interval lengths. And each function value multiplied by interval length is the area of a rectangle. As our interval lengths get smaller, our estimate of the area from the sum of the areas of the rectangles, that gets closer and closer to the true area under the curve. For a non-negative continuous function, if we construct a Riemann sum of the function, so for a non-negative continuous function for a positive function, if we construct a Riemann sum of the function, each non-zero f of ck multiplied by delta xk term is the area of a rectangle reaching from the x-axis to the function curve. And the Riemann sum, the sum of those f of ck times delta xk terms, that is the sum of the areas of the rectangles. As the rectangles give an increasingly good approximation of the area under the curve, as we use smaller and smaller subintervals, we call the limiting value the area under the curve. So for a non-negative continuous function, for a positive continuous function over a closed interval, the limit as the subinterval lengths approach zero of the Riemann sum of the function is equal to the area under the curve. And written here in mathematics, we have the limit as the norm of the partition approaches zero of the sum from k is equal to 1 to k is equal to n of f of ck times delta xk. That's equal to the area under the curve. So that limit of a Riemann sum, that's equal to the area under the curve. And this is the definite integral of the function over the interval. For a non-negative continuous function over a closed interval, the area under the curve is the definite integral of the function over the interval. As we continue with further videos, we'll develop this further. Thank you for watching. I hope you enjoyed the video, and see you next video.